Okay, the typical Pythagorean theorem states the area of the square built upon the hypotenuse of a right triangle is equal to, okay, and we know the what you're talking about, right? This area is sum of those two, right? So when you look at this Pythagorean theorem, the concept, the formation is like this. The condition is the given triangle must be a right triangle. Okay, ABC. Then, for those given condition, c square plus c square, the square of the hypotenuse, is sum of the square of the length of the other two legs, right? And in math, we always interesting about the converse of it. Whenever we have any conditional statement, and if it's true, or even in the first case, still we are interesting about how about the converse. Okay. So the next possible question is for any triangle, we don't know whether it's a right triangle or not. And somehow we got c square equals a square plus b square. Okay. Then can you say that triangle is actually right triangle? Okay. Like that, right? And actually it's true, right? So the more general statement of Pythagorean theorem is if and only if, right? If a right triangle is given, then we have that equation. And for any given triangle, if we have that equation is true, then the triangle must be a right triangle, either way. Okay? So let's look at the next theorem, or actually explanation, but it's like this. It says a triangle with those sides is a right triangle. So we have those three sides. So when you start it, it just says a triangle. We don't know whether it's right triangle or not. And it claims if any triangle has those three numbers for the size of three sides, right? Then that triangle must be a right triangle. And the proof is sum of the square of two smaller numbers equal to the square of the largest number. Then that must be right triangle. And the reason for that, the reason behind that claim is because of the Pythagorean theorem, right? So the question of this example is critical about this proof. You can say, if the statement is like this, right? Then this is only one-way statement, right? Only this way. So it only guarantees if it's a right triangle, then we have that relation among those sides, right? It doesn't claim the backward, the converse, but in this proof, in this example, actually this person used that Pythagorean theorem, but actually reverse way, right? Because that expression is working, therefore the triangle must be a right triangle. It's not true, okay? Because the statement itself is only one direction. So if you want to use this one, and it's really true, this statement should be written differently, right? Then that proof is okay, right? Because the statement says if and only if. You follow me? So in math it's really picky, right? So math people are really picky. So the reason is like this. Let me say this way. Okay, let me. If x is 2, then x is a prime. Okay? Yeah, we are familiar with that. So that statement is true, right? Then let's take the converse of it. If any number is a prime, then that number is number 2. How about that? No way, right? We have infinitely many different prime numbers, which we are going to cover later. But, okay, any prime number is always 2? No, it's not true, right? So in mathematics, we have many such cases. Only one direction is true and the other one is not true. Okay, so we should be very careful about that statement, right? And that's why in math, in many cases, when you prove that conditional statement P implies Q, then we always interested about how about the converse of it, whether it's true or not, like that, right? Now, be careful. Pythagorean theorem is actually true for both directions, okay? So this proof should be okay, right? But the only problem is if your theorem, the Pythagorean theorem, states only this way, one way, then you cannot use this one directly. So in math book, they always have some kind of corollary or another theorem shows the other direction too, right? Then when you prove this type of question, then you have to use not the Pythagorean theorem directly, but the other one, right? Okay. Or in your Pythagorean theorem, it should state if and only if, both directions. Okay, so just be careful. But now let's just focusing on several different proofs. And when you're googling it, I think there are about more than 150 different types of proof for Pythagorean theorem. People really prove a lot different ways for this one. So let's just check some of them. And the following one, we believe, is actually the Pythagorean actually use this concept, this method. Okay, so let's just try to prove using this method. Okay, so our concept is like this: when you compare these two diagrams, the area of this square should be same because all the sides are a plus b and a plus b, right? And even that is true for both, right? Okay, small different arrangements, but same thing, right? So the area must be same. So we are familiar with this style. Okay, it's good. So let's just look at algebraic way. Of course, everything depends on how, but when you look at the left hand side, each side is a plus b, and we have both of them for base and height, right? So the area of the left hand side figure, we can simply say a plus b entire square. Good. On the right hand side, let's just break down into several pieces. We have this small square, c and c, so it's a c squared. And we have that right triangle, four of them, and they are all exact same right triangles, right? Like a base is b and height is a, like that, right? So we have four of that triangle, right? Let's say b and a. Okay, so we can say it's 4 times area of triangle, and if it's a right triangle especially, then just base times heights divided by 2, right? So we can say that is c squared plus 2ab. Okay, in the left hand side, when you pull out by distribution law, it's a squared plus 2ab plus b squared, right? So we got the same thing, which means what? After cancel out this 2ab, we get that Pythagorean theorem by that, right? So using just this one, we can explain it like that, right? I only show the equations, but you can explain it that way. Okay? And you can explain that one graphically, like when you just compare these two figures from both sides. We already know the areas are same. That's the given condition like that. Then in this case, let's look at remove that right triangle. Okay, that's the right triangle with base b and height a, right? Then this one is exactly same one, right? Congruent. So, and we are having this. So let's remove these 4 small right triangles from the left hand side figure. Then that's left over, right? But from right hand side, we just remove those 4 corner triangles, right? And they are exactly matching each other, right? So this one is same as that, this one is same as that, like that, right? You can matching them. So we remove exact same figures from both sides, right? Then the leftover figures, the area should be same, right? And the left-hand side is a squared plus b squared. Right-hand side is simply c squared, right? That's how you got that. Okay, okay, let's prove a little bit different way. Now this one is a little bit more complicated to follow, but it's also similar. Okay, here this is done by Bhaskara, okay, around 12th centuries, right? But he gave this type of proof, okay, geometric approach, like changing the left-hand side ones to the right-hand side ones. And the condition here is, let's say the base and heights of this square is c, same c, and for that small length is b, and this large one is a. Okay? And same thing for everywhere. Okay? So you can see that is also b, and this is a, right? And that is b, all together like that. Right? And try to rearrange these pieces into like that. So it's clear, like this one, that one together is here, and this one, that one together here. Then this middle square, it's placed here. Okay, good. And just try to cut this portion, right? Like that. Then when you look at this given one on the left hand side, whenever you look at any right triangle like this, the base is B and the larger one is A temporarily. So this one is A and that is B. Same thing happens B and A, right? Then that should happen here too, right? So the smaller one is B and the larger one should be A, right? Then when you look at this, in the middle, that small square, each side has A minus B, right? Because that is A and this is B. So left over is A minus B. So we know this is A minus B and that is A minus B, right? And because that side is A and this is B, then it's matching with this one, right? A minus B. So we know these heights must be same, right? Okay, by that way. And because of that, when you cut down this, that length for this portion is A minus B from A, right? So this leftover part is A minus B, right? The entire length is A and minus A minus B, which is B, right? Okay, so this portion, height is B and base is also B. Another thing is, we know this is B, right? And that is A minus B. So when we add this together, the sum is A, right? So height is A, and that side, the base is B. Oh no, A, another A, right? So when you look at this right-hand side figure, it's A, and B, right? But there's nothing added or deleted, right? When you rearrange these pieces to the right-hand side, right? So this one is just C squared, and the rearranged ones has A squared plus B squared, and they should be same area.